Hey there, welcome to Electron Configuration Part 2. Okay, so hopefully you were wondering as you were doing electron configurations, what do we do when we have elements that are all the way like at 109? What does that electron configuration look like? Well, it looks really, really long. Eventually you'll get to the point where you've got these orders memorized, like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and so on. But there is a shortcut, thankfully. We call this the noble gas notation, or electron configuration shortcut. So in order to be able to do this shortcut, you have to know what a noble gas is. And so a noble gas is a very unreactive element that has a full energy shell, or its sublevels are full in terms of its s and p orbitals. And so what we're going to do is we're going to take our periodic table and we're going to mark down where the noble gases exist. And that is in group 8A. So we have helium, neon, argon, krypton, xenon, radon, and so on. As far as our noble gas helium, it's full with 2 valence electrons. And neon is full with 8. So is argon, so is krypton, and so is xenon, and so on. Alright, so what we're going to do is we're going to take our configurations, we're going to use a noble gas that has slightly less electrons than the element that we have, and we're going to say that it has all of the electrons that are present within that noble gas, plus a few more. So here's our first example, silicon. Alright, so here, this is where it's located on the periodic table. I'm going to tell you we're going to go up and over to the right to find the noble gas that has less electrons than silicon has. So up into the row above it, all the way to the right, would mean this noble gas. What is that? That's neon. So what we're going to do is we're going to put neon in brackets. We're going to say that silicon has all of the electrons neon has, plus some more. So we have to step off of, instead of hydrogen now as our starting point, now we're starting at one of the noble gases. So neon is our starting point for this one. So we count after neon, so that goes into the third row, S block, 2 steps, and then into the row, P block, 2 steps. Okay, so that shortens it up a little. All right, we'll try another one, germanium. So up and over to that noble gas, that is argon. So put argon in brackets. Now our starting point is after argon, so we write argon down, and then we're in the 4th row, S block, 2 steps. This is the 3D, 10 steps. And then to get to germanium, we're back to the 4th row, P block, 2 steps. Okay, so it should seem easier than even yesterday. All right, so last example, cesium. So again, we go up and over to find the first noble gas over here, and that is xenon. Step off of xenon to get to cesium, so that's in the 6th row, S block, 1 step. All right, one question that students always have is, what if I need to write the noble gas notation for a noble gas? Do I just put that noble gas in brackets? Like if I had xenon, would I just put xenon in brackets and say I'm done? Nope. What you would do is you would still go to the noble gas before it and then go from there. So if I had xenon, I would start here at krypton and then add in until I got all the way to xenon. All right, so let's talk about going through the F block, because remember the F block has been removed from the periodic table. And so in order to do that, we're going to have to travel through this little dark space over here. All right, so let's say we have to do cerium. So that is actually in the 6th row. That's the 7th row. And so here it is. When we go up and over, we have to imagine that it's in the 6th row. So we're going to go up and over to the 5th row, since it's in the 6th row. and that noble gas is xenon. Okay, we step off of xenon, 6th row, S block, so that's 6s2. Then what we're going to do is we're going to step onto the 5d, one step, and then we don't go through the D block again, we just go simply straight down through here into, this would be normally 6F, but F block is behind by 2, so that would be 6th row minus 2, so 4F and one step, so 4F1. All right, let's try uranium. That's right here. This is in the 7th row, so we're going to go from the 7th row to the 6th row to find the noble gas, and that is radon. Then we're going to step off of radon onto the 7th row, S block, 7s2. Then we're going to step onto 6th row, or excuse me, 7th row, D block, so it's behind by 1, 6d, 1. And then now we're going through here onto the F block. It's behind by 2, so that's 5F. So it's 5F, 1, 2, 3. All right, one more. Now, what happens if you have to go through the F block, but you're located somewhere right here? It's a little trickier, so let's do that. So TA is right here. Go up and over to xenon. Step off of xenon, so that's 2 steps in the 6s, so 6s2. Now we step onto the 5d1, so I'm going to write that down. And then we go down to the F block. We have to go all the way through that. So we can't just jump from here to here. We have to go down through the F block. So that is 14 steps across the F block, and that's 4F14, because F is behind by 2. All right, so then we step off of this one, which happens to be atomic number 71, and we step onto atomic number 72, hafnium right here, and that's 1, 2 steps. So that would be 5d2. Now you can't leave these two D's separated like this. Okay, so I would like you to rewrite it as soon as you see that. So I'd circle these two and rewrite it so that the D block elements are combined. And you would put them at the end. And you put them at the end because that helps you to figure out what the element is. Because that last electron configuration at the end, the row, the block, the number of steps can pretty much tell you where that element's located. So we'll cross that out, combine them, so it just looks like this. Xenon, 6s2, 4f14, 5d3. Now you can, once you get used to these, just go, I'm gonna have to come back to this one, so I'll go from here, down here, then go back and count the 5d and so on. Now that doesn't happen when you're like the past two examples. You never went back to the D, but when you're over here, you have to go back to the D block. All right, so with some of the things that we're learning now, you're going to learn that there are exceptions to some of the rules. And I'm only going to teach you a few of the exceptions that happen. Our first exception is when you have a full sublevel, like copper, or almost full sublevel. All right, so if I were to do the electron configuration for copper, I would go up and over argon, 4s2, 3d9. And that's where I would find copper. However, when we test copper, what we end up finding is instead it looks more like this. It has 4s1 and then 3d10. And so we need to know why that happens. What happens is the D block orbital here is so close to being full. And remember, these are pretty close in energy. This is just slightly less energy to put an electron here. So what happens is the electron is stolen from the s orbital to put into the d orbital so that the d orbital is full, or all of the d orbitals are full. And so we get this 4s1, this lonely s electron here. And so copper gains stability by having a D sublevel that is full. Another exception is chromium. When we draw it out just normally using our periodic table, it looks like this. Argon 4s2, 3d4, but it actually has this electron configuration. And so why does that happen? Well, in chromium, it has an almost full, half full, D sublevel. And so in order to fill it, it takes an electron from the 4s. One reason it also does that is because in this one, these two are sharing this orbital and electrons repel each other. So it's less energy to put it over here where it's not repelling here. Also, it's stable because it's halfway full. Okay, so this is just the D block section of the periodic table. I would like you to put a star next to the exceptions that you need to know, and they are right here. So put a star next to these five, and label exceptions right here. These are the exceptions to the Aufbau principle. They fill up just a little bit differently, and there's some stealing that occurs. And they tend to happen when D is either 4 or D is 9. So we're going to write that right here in your notes. It says steal when D is 4 or 9 only. And I went ahead and pointed out exactly which ones steal, because this one is a D4, but it does not steal. I probably won't put this one on a quiz, but I will put one of these 5 on a quiz. So this is when D is normally 9. It steals one from the S. All right, so last part are the electron dot structures, also called Lewis dot diagrams. Okay, well, before we get into this, we need to know something about the atom. So I've drawn pretty much a Bohr diagram. And so within this, you have valence electrons. Now, valence electrons are the electrons in the outermost energy level. They have the highest amount of energy because they're furthest away from the nucleus. Okay, so those are the valence electrons that sulfur has. It has 6 valence electrons in total. These are just the core electrons. They're the ones on the inside. Note that elements do not have more than 8 valence electrons. This is because we're only pulling from the highest energy levels, and the highest energy levels occur only in the S's and the P's. Remember that D block is behind by 1, and F block is behind by 2. All right, let's do an example with sulfur. I went ahead and wrote down the noble gas notation for sulfur. I could have also done the full electron configuration, but this one's faster. This is the one I did. What you're going to do is you're going to find the highest energy level. Remember, the energy levels are the n numbers or the coefficients in the notation. So the highest number for the coefficients is 3. This one is in the 3rd energy level. This one is in the 3rd energy level. This is in the 3s sublevel. This is in the 3p sublevel. Okay. So I'm going to underline the 3s to show these two highest energy level. Then I'm going to circle the electrons that are in it. Those are the exponents, so here and here. So altogether, sulfur has 2 from the S and then 4 from the P orbitals. And it's always a combination of your S and P's in your highest energy level. Okay. So 2 plus 4 gives me 6 valence electrons. So sulfur has 6. You're going to draw those around the atomic symbol of sulfur. And so that's S. And then you're going to do these in a particular pattern. You're going to do 6 dots, but you're going to go all the way around first and put 1 on each side of the 4 sides of this symbol. So 1, 2, 3, 4. And you're going to do that before you ever start pairing them up. And then 5, 6. So you'll notice that I have 6 valence electrons around this sulfur. And there's 2 spots missing where I could put 2 more because the maximum is 8. And what that is going to tell us later is that sulfur has 2 places where it can bond. Alright, so next one. This is the electron configuration with the noble gas shortcut because it's faster. We're going to look at the highest energy level. That's the 5th energy level, not the 4th one. And there are 2 valence electrons. So I'll just put the symbol and 2 dots. Notice I'm going to keep them separate. All right, that's it. Hope that helped.